In part one of the preceding tutorial, we looked at how forces affect motion from a qualitative or conceptual standpoint. In this part of the tutorial, we're going to look at how forces affect motion from a much more quantitative perspective. Since here we're going to be talking quite a bit about forces and accelerations, I want to first remind you about the units of force and the units of acceleration. The units of acceleration are measured in meters per second squared. And one of the things that we're going to do in this tutorial is help build up an intuitive feel for what this actually means. The units of force are measured in newtons, denoted by the symbol N. And moreover, since F equals ma, in other words, when you apply a force to an object, it responds by accelerating, the units of force are in newtons, and the units of mass are in kilograms, and the units of acceleration are in meters per second squared. So it must be the case that 1 newton, the unit of force, is the same as 1 kilogram meter per second squared. Our main focus in this part of the tutorial will be how objects move when they're subject to a constant force. And we're going to focus exclusively here on one-dimensional motion, so objects moving along a straight line which are subjected to a constant force. And by constant force, I mean a force which is always points in the same direction and always with the same strength. So let's consider the following scenario. Suppose we have an object here. It's a 2 kilogram mass. It's initially moving to the right at 3 meters per second. It's starting out at the 6 meter mark, and you're pushing on it with a 10 newton force to the right. Well, we've seen previously that when you push with a force in the same direction that the object's already moving, the object is going to go faster and faster and faster. So, let's examine what happens in this case. Let's start with the block's acceleration. This block here, since it's a 2 kilogram mass and there's a 10 newton force acting on it towards the right, in other words in the positive x direction, we can describe the block's acceleration as 5 meters per second squared in the x hat direction. Let me remind you where this comes from. We know that the acceleration of an object is given by its force, the force acting on it, divided by the mass of the object. In this case, the force acting on this block is a 10 newton force in the positive x hat direction. And the mass is a 2 kilogram mass. So 10 divided by 2 gives us the 5. Here we have newtons per kilogram. That's the same thing as a meter per second squared. And the direction is in the x hat direction. Notice that the direction of acceleration of any object is always in the same direction as the force. So in this example, there's a force to the right in the positive x direction. Therefore, the block's acceleration is also in the positive x hat direction. So what does this actually mean when we say the acceleration is 5 meters per second squared? What does that mean? Well, it means that the block's speed in this case is going to change by 5 meters per second every second. An acceleration of 5 meters per second squared means that with every passing second, the block's speed is going to change by 5 meters per second. So it's called 5 meters per second, hence the acceleration is expressed as 5 meters per second squared. But this is the meaning of what the acceleration is doing. It's changing the block speed by 5 meters per second every second. So let's fill out a little chart here. At time 0, that means right at the start, the block, we're told, is moving at 3 meters per second to the right. So its velocity is 3 meters per second in the positive x hat direction. But because the acceleration of the block is 5 meters per second squared in the x hat direction, that means with every second that goes by, the block is going to gain 5 meters per second worth of speed. So after 1 second, the block is now moving 5 meters per second faster than it had been namely 8 meters per second in the x-hat direction. After another second goes by, it will be moving at 13 meters per second in the x-hat direction. After another second goes by, 18 meters per second. After another second, 23 meters per second. So that's the meaning of acceleration. 5 meters per second squared means that it's changing its velocity by 5 meters per second with every passing second. Now, if you stare at these velocities at different moments in time, we can construct a general expression giving us the velocity of this block at any moment in time. It's going to be equal to its initial velocity, the velocity it starts with, plus the acceleration, 5 meters per second squared, times the number of seconds that have elapsed. So, for example, let's say we wanted to use this formula to find the velocity at time 2 seconds. So we'll just plug in t equals 2 seconds here. We'll get 3 meters per second plus 5 meters per second squared times 2 seconds. That will give us 3 plus 10, 13 meters per second in the x-hat direction. Let's look at another example to get a little bit more intuition. This time let's consider an object here. This one is traveling initially to the right at 15 meters per second. It's starting at the 6 meter mark. However, this time we're pushing on it to the left with a 10 Newton force. So let's think about what's going to happen here. The block is moving to the right at 15 meters per second initially. But because we're pushing it to the left, we're pushing it opposite to the way it's moving. That means the block is going to slow down. So the block is going quickly here. It's going to slow down, slow down, slow down, stop momentarily. And since we're continuing to push, it's going to then start building up speed faster and faster and faster in the opposite direction. So now let's analyze this situation. The block's acceleration. Well, there's a 10 Newton force to the left. In other words, the force is in the negative x-hat direction, and the mass is 2 kilograms. So the block's acceleration is going to be negative 5 meters per second squared x-hat. Once again, the way that we get that is as follows. The acceleration of an object is given by its force, or the force acting on the object, divided by the mass. The force in this case is 10 newtons in the negative x-hat direction, to the left, and the mass is 2 kilograms, so that gives us an acceleration of 5 meters per second squared in the negative x-hat direction. As a reminder, the direction of the force dictates what the direction of the acceleration is going to be. So if the force is in the negative x-hat direction, the acceleration is also going to be in the negative x-hat direction. Now let's think about what this acceleration implies for the velocity. An acceleration of negative 5 meters per second squared means that the block speed is going to change or be reduced by 5 meters per second every second. So negative 5 meters per second is how much the block speed is going to change by with every passing second. So it's negative 5 meters per second per second. So let's fill out this chart. Initially, at time 0, the block is moving at 15 meters per second in the positive x-hat direction. But because it has an acceleration of negative 5 meters per second squared, with every second it loses 5 meters per second worth of speed. So after 1 second, it's down to 10 meters per second, still traveling to the right. After another second, it's slowed down, and it's now only moving at 5 meters per second. After another second, it's momentarily stopped. After another second, since we're still pushing on this object, it's now going to start traveling to the left at 5 meters per second, but it's moving in the negative x-hat direction. I'd like you to stare at this chart for the velocity here. And now let's go ahead and write down a general expression giving us the velocity of this block at any moment in time. So the velocity of the block at time t is going to equal the starting velocity, which is 15 meters per second, minus 5 meters per second squared, that's the acceleration, times the number of seconds that have elapsed. So for instance, let's see what happens at time t equals 2. If we plug in t equals 2 into the velocity, we'll get 15 meters per second minus 5 meters per second squared times 2 seconds. That will give us 15 minus 10, which is 5. So it will give us 5 meters per second in the x-hat direction, and that's its velocity. We can now generalize these preceding two scenarios as follows. Suppose we have a block of some arbitrary mass m, and it's subjected to some constant force F. Its initial velocity is v0, and its starting position is x0. So let's visualize this motion here. This block is going to go faster and faster and faster to the right there, and let's write down how its velocity is going to change in time. First, let's get the acceleration. The acceleration is given by the force acting on the object divided by its mass. So this represents its acceleration. Once we know that the acceleration a, then we can say that the velocity of this object at time t is going to be given by whatever velocity it started with plus the acceleration times time. The acceleration times time, this term represents how much the velocity has changed by owing to the fact that the object's accelerating. So the velocity at time t is equal to the starting velocity plus the acceleration times time. Two remarks that I want to make about this equation. First of all, this does describe the velocity of an object at any time, provided the object is subject to a constant force. If the force on an object is changing, it's either changing in the direction or it's changing in size, then this expression is simply inaccurate. It does not apply. It only applies when you have a constant force and hence a constant acceleration on an object. The second comment that I want to make is, in this scenario here, notice that all the motion was purely along the x-axis. It was purely horizontal. There was no motion in the vertical in this particular example. So this expression here, it's written in vector form. The velocity vector at time t is equal to the starting velocity vector plus the acceleration vector times time. But since in this case all the motion is purely along the x-axis, we can just take the x component of these vectors. So instead of writing the velocity vector at time t, we can just write the horizontal component or the x component of the velocity at time t. Instead of writing the initial velocity vector, we can just write the initial horizontal velocity. Instead of writing the acceleration vector times t, we can just write the horizontal component of acceleration times t. So this is perfectly good whenever the object is moving purely in a single direction, like the x direction. This is slightly more general, but often, if the object's moving in just along a straight line, this will suffice. Now, we've just seen that when we have an object subject to a constant force, it's going to accelerate and the velocity is going to change, and the velocity at any time can be found by this expression. But we might ask, well, where is the object going to be at any time? After all, this object's moving along, so its position is changing. What is its position as a function of time? How do we compute that? Well, there are two methods for finding the object's position as a function of time. One method uses a derivation based in calculus, and the other doesn't use calculus. They both lead to the same final result, so it doesn't matter which one we use to get there. The net result will be the same. But I want to show you first the calculus-based method, and then I'll show you the non-calculus-based method. So let's start with the calculus-based method. Here we have our object subject to this force. It's going to be accelerating to the right, And we've already discovered that its velocity at any time is given by this expression. How are we going to find its position at any time? Well, recall that the velocity, the definition of velocity is it's the rate of change of position. Or more precisely, velocity equals the derivative of the position. So since velocity is the derivative of position, we can write the position as the integral of the velocity. So if I want to find the position, I just have to integrate this expression for the velocity. If I go ahead and do that, this is what I'll get. The position of the object at time t is given by these three terms. Let me focus first on this middle term, v naught times t. So go back here. This is the initial velocity. If I integrate this with respect to time, this is a constant, so an integral of a constant with respect to time is just the constant times time. That's where this term comes from. Now let me show you where this term comes from. I'm going to take this term here, a times t, and integrate it. But a is a constant. So the integral of a constant times time is the constant times time squared over 2. So that's where this term comes from. What about this term? Well, you may recall that any time you do an integration, there's always a constant of integration. So I'm calling the constant of integration here r naught. R naught actually has a nice physical interpretation. R naught that appears in this equation here tells you or represents the initial position of the object at time 0. So, in other words, the position of the object at time t is equal to its starting position plus its initial velocity times time plus 1/2 its acceleration times time squared. So there you have it. When an object is subject to a constant force, this expression tells you the velocity of the object at any time, and this expression tells you its position. Now, if you're dealing with the case where the object is moving along a straight line, as in this example, where it's moving purely along the x-axis, then it's often more convenient to just focus on the x component of the velocity and the x component of the position, since all the action is happening along the x-axis anyway. So I can rewrite and just these expressions just by focusing on the x component of them as follows. This first expression becomes, instead of the velocity vector, I have the x component of the velocity. Instead of the initial velocity, I have the initial x velocity, or horizontal velocity. Instead of the acceleration times time, I have the horizontal acceleration times time. Likewise, in this position equation, the position, the x component of position, I'll write that as x of t. This represents the initial position of the object at the start. Well, I'm going to call that x naught here. This is the initial horizontal position. Instead of writing the initial velocity vector, I'll write just its x component. This is the initial x component of the velocity vector times t. And likewise, 1/2 the acceleration times time squared becomes 1/2 the horizontal acceleration times time squared. So as I said, this is appropriate if your equations, or if the motion of the object is purely along one direction, like the x direction, for instance. And just as a reminder, these boxed equations, they only apply, they only describe the velocity and the position of an object if that object is moving subject to a constant force. If the force is not constant, then these expressions are incorrect. They do not apply. Now, I promised you that I'd show you how to derive this same expression using a non-calculus method. And let me do that for you now. So, we have our object here subject to a constant force. It's going to go along and accelerate. We know its velocity is changing in time according to this expression. So at the beginning, at the start, at time 0, the velocity of the object is v naught. That's its starting velocity. At the end of the motion, let's say at a time t later, the velocity of the object, the new velocity, is now the initial velocity plus the acceleration times time. It's faster than before. So here's the velocity at the very beginning at time 0. Here it is at the later time t. So during the course of its journey, the average rate at which it was moving, well, I'm going to average these two expressions here. So I'm going to take the average, 1/2 of the initial velocity and the velocity at the beginning and the velocity at the end. So I'm going to, here's the average. And if I write this out, this can be written as v0, the initial velocity, plus 1/2 at. So this is the average rate at which the object traveled during its journey. It started out slow, it ended going fast, and this was the average rate at which it traveled. So the distance covered by this object as it traveled is its average rate times time. And its average rate is this times time. And if I simplify this expression, this just becomes v0t plus 1/2 at squared. So this represents how far the object traveled during its journey. So if I want to write an expression for the object's position as a function of time, the object's position at time t is equal to its starting position plus how far it traveled during its journey. That's this part, namely this. So, in summary, when an object is subject to a constant force, this expression tells us what the velocity is as a function of time. This expression tells us what the position is as a function of time. Two reminders, though. First, once again, I want to reiterate that these expressions are only valid if the force pushing on this object is constant, namely that this force never changes size and it never changes direction. If that's the case, then these expressions tell you what the velocity and position of the object will be. If the force changes, then these equations do not apply. Second thing I want to remind you of is that if the object is purely along one direction, like one axis, in this example it's purely along the x-axis, then in that case we can just take the x component of these equations and they become this. Now, sometimes it's easy to get caught up in the mathematics and you begin to lose sight of what these things actually mean, like what are all these terms and these expressions. So I want to go over a quick interpretation of what this means. So here is our basic situation that we're considering. Here are those two equations giving the position and giving the velocity and the position as functions of time. Let's interpret this. This term tells us the object's position, the object's velocity at time t. Well, what does it depend on? The object's velocity at time t depends on its starting velocity, that's this term, this is the initial velocity, plus this term represents how much the velocity is changed by because the object is accelerating. After all, you're pushing on this object with a force. We know that's going to cause its velocity to change. In other words, it's going to be accelerating. So this term here tells you the starting value of the velocity, and this term tells you how much it changes by. So the final velocity is equal to the starting velocity plus how much it changes by due to the acceleration. Next, let's look at this position equation. This term here tells us the object's position at time t. What does it depend on? It depends on where the object starts. So x0 represents the starting position of the object. This term here has a nice interpretation. It means the following. Imagine this object was initially traveling along at speed v0, but there was no force on it. So that means the object is going to continue to travel at that same speed v0. So its position is changing because it has some initial velocity. This term tells you how far the object travels just due to the fact that it has some initial velocity. This last term here tells you the extra distance that the object travels because, in fact, there is a force on it which is changing the velocity of the object. So this is the extra distance traveled due to the fact that the object's velocity is changing. So again, the object's position at a time t is given by the object's starting position plus how far it travels due to the fact that it's got some initial motion, plus how far extra it travels due to the fact that it's being pushed, so its velocity is changing. So these are the two main equations that you'll work with when you're solving problems in which the force acting on an object is constant. But sometimes in your physics class or in your physics textbook, there'll be a third equation that's introduced. And this third equation, which I'll present to you in a moment, isn't actually new in the sense that it doesn't give you any new or additional information. If you never heard of that third equation that I'm about to present and you only knew these two, you'd be able to solve all the constant force problems you wanted. But sometimes that third equation can be convenient. And the way it's derived is as follows. If you take this first equation and solve it for t, and then take that expression for t and plug it in to the second equation here and here, then that second equation can be rewritten and it takes the following form. It says v of x, this is the final velocity squared, is equal to the initial velocity squared plus twice the acceleration times the final position minus the initial position. Okay. Again, this equation is just completely derived from the preceding two equations. It's not new, but it can be convenient because in some problems, maybe you don't know you're only given like an initial position and a final position and an initial velocity, and you want to find the final velocity or something like that. In other words, sometimes you're not given any time in the problem explicitly, and you see that this equation is convenient because it doesn't depend on time explicitly, whereas the preceding two equations do. Okay? If this is a little vague right now, that's okay. When we do the practice exercises a little bit later on, you'll see this in action. But as I said, this isn't some deep equation in physics. The other two equations that we just derived, those tell you everything you need to know about constant force problems. Well, it's time to start looking at some actual examples and work out some problems together. So before we do this, you may actually wonder, well, do constant force problems actually occur in nature? And the answer is most definitely yes. One of the most common examples is an object that's being pulled by the force of gravity near the surface of the Earth. So for example, if I take a ball and drop it, you know that there's a force of gravity tugging it down. I'm going to ignore any air resistance that the object might feel as it falls. So the main force acting on it is the force of gravity. Gravity exerts a downward force on the object, and it's going to cause a downward acceleration. And the size of that downward acceleration is approximately 9.8 meters per second squared. So this number arises so often that we give it a name, we call it g. So little g represents the acceleration of an object which is in free fall near the surface of the Earth. And the value of little g is 9.8 meters per second squared. So the force of gravity near the Earth is approximately constant. It's downwards, and it creates a downward acceleration of size 9.8 meters per second squared. Well, you might say, well, where did this come from? For the time being, just accept it as an experimental fact. In your physics course, your professor will likely take you through a more detailed derivation of it. But for now, we're going to treat this as an experimental fact that any object that's in free fall, and by free fall, it just means that an object on which gravity is pulling and there's no other force pulling. So if I drop a ball, as it's falling down, if I ignore air resistance, then it's in free fall. if I toss a ball up into the air, once it leaves my hand, even though it's traveling upwards, gravity is still pulling down, so the object is still considered to be in free fall, and it's still experiencing a downward acceleration of 9.8 meters per second squared in the downward direction. So this is probably one of the most common cases where you're going to analyze a problem in which the acceleration is constant, or the force is constant. So now we'll look at a few examples. The first example actually doesn't involve the force of gravity, but the second example that we look at will. So here's our first example. Suppose we have a particle, it's an electron, and it's initially, in other words at time 0, it's sitting here at the 2-meter mark. And it's actually moving with some initial velocity of 10 meters per second to the right. So in other words, at time 0, you have this particle here at the 2-meter mark traveling to the right at 10 meters per second. However, we're going to assume that this electron is subject to a leftward force. I haven't drawn in this picture here, I haven't drawn in the leftward force, but imagine that there's a leftward pointing force acting on this object that's going to be slowing it down, and it's going to cause it to accelerate at a rate of 8 meters per second squared to the left. Okay, let's analyze the behavior of this electron. Okay, so let's start by saying, how is it going to move? Let's just think about the motion. So the particle is here. It's initially moving to the right at 10 meters a second, but there's a leftward force on it. So what that means is that as the particle is moving to the right, it's going to slow down, slow down, slow down, momentarily stop somewhere, then start, since the force is still pushing to the left, going faster and faster and faster and faster and faster. That's what's going to happen to this electron. Okay, now let's go ahead and write down the equations describing the electron's position and velocity as a function of time. So, on the preceding pages, we had general expressions for what the position as a function of time was and what the velocity was. Now let's apply it to this scenario. Let's look at our expression for the position as a function of time. The position at time t is given by the starting position, which in this example is 2 meters, plus the initial velocity times time. In this example, the initial velocity is positive 10 meters per second times time. And then this last term here, this is the 1/2 acceleration times time squared term. But the acceleration is negative 8 meters per second squared here, because it's 8 meters per second squared, but in the negative x-hat direction, because we're told that the force is to the left. So the 1/2 acceleration times time squared becomes 1/2 times negative 8 meters per second squared. That gives us negative 4 meters per second squared times time squared. So that's where each of these terms came from. Likewise, if we go to the velocity equation, the velocity at time t is equal to the initial velocity, which is 10 meters per second in the x direction, plus the acceleration times time. And the acceleration in this case is minus 8 meters per second squared, since it's to the left. Okay? So these two equations tell you where the particle is and what its velocity is at any moment in time. Next question. What is the rightmost point reached by this electron? So after all, when we visualized the motion, we said it was going to be moving to the right, but slowing down, slowing down, slowing down, momentarily stopping, and then going faster and faster and faster to the left. And we want to know, how far does it go before it turns around? What's its rightmost point? Well, at the rightmost point, that means it's momentarily stopped. It's starting to turn around. So what we can do to find that rightmost point is we'll go to the velocity equation and we'll set the velocity equal to 0, because at the turning point, it's momentarily stopped. Its velocity is 0. So we plug in 0 here, and we get 0 equals 10 meters per second minus 8 meters per second squared times t, we can solve for t. And that time that we get, 1.25 seconds, that's the time when this electron reaches its rightmost position. And now that we know that time when it's at its rightmost position, let's plug into our position equation here. Just plug in 1.25 seconds in for t here, and that will tell us where it is at that time. And if we do that, you'll find that you get 8.25 meters. So the turning point is way over here at about 8.25 meters. Next question. What is the particle's acceleration at its rightmost point? So remember this particle, this electron was going here, slowing down, slowing down, slowing down, momentarily stopping, then going faster and faster and faster in the opposite direction. So right at that turning point, when its velocity was 0, how fast, what was its acceleration? Now this is a point that students often find confusing, because you might be thinking, well, if right at that turning point it's not moving, it's momentarily not moving, if the velocity there is 0, then how can it have any acceleration? But you have to remember, acceleration and velocity are not the same thing. Acceleration represents a changing velocity. So you have to ask, when the particle is here at its turning point, is the velocity still in the act of changing? And the answer is yes. How do you know that? Because right at this moment, let's say the velocity is 0, but a billionth of a second later, it's going to be moving to the left because there's this force pushing on it. And so even though right at a given moment it was momentarily stopped, that doesn't mean it wasn't accelerating. After all, we were told in this problem that the acceleration is constant. It's a constant value of 8 meters per second squared to the left. So the acceleration throughout this entire problem, no matter what the velocity of the particle is, no matter where it is, no matter how fast it's moving at that time, it's always 8 meters per second squared in the negative x-hat direction. That's what we mean by a constant acceleration problem. A perhaps somewhat more intuitive way of seeing how the acceleration can not be 0 when the velocity is 0 is as follows. At the turning point, the velocity is 0. We're agreed on that. However, think about the force. There's still a force on this thing pushing it to the left. And what do forces do? They cause accelerations. So there's still a force acting on the thing, hence there's still an acceleration. And so even though it's not moving right at that instant, it's still accelerating. Finally, let's ask the question, what is the electron's velocity when it reaches the origin? After all, this electron is going to go here, slow down, momentarily stop, then start going this way faster and faster and faster and faster. And when it passes through the origin, passes through the x equals 0 mark, what is its velocity at that point? Okay. Well, let's see. We expect the velocity to be negative because it's moving to the left. Now let's see if we can figure it out. Well, we want to know the velocity when it's at x equals 0 as it's passing through the origin. So what we're going to do is this expression up here tells us the position at any moment in time. So we're going to set the position equal to 0 and solve for the time when it reaches the origin. So if I set x equal to 0 here, I get this equation. This is a quadratic equation. I look up the quadratic formula and I find that there are two solutions to the equation. One is t equals 2.69 seconds. The other is a negative time, negative 0.19 seconds. We can throw out this extraneous solution. It's not physically relevant. And so what we're claiming here is that at time t equals 2.69 seconds, the particle is here. In other words, it took 2.69 seconds for the particle to go from here and then back to there, to the origin. And now we know how long it took to get to that point. Then we can plug that time in, that 2.69 seconds, into our velocity equation, and that will tell us its velocity at that time. So if we plug in that value of time into our general velocity equation, we end up with a negative 11.5 meters per second. That means the particle, when it reaches the x equals 0 mark, the origin, is moving to the left at 11.5 meters per second. Before moving on to our next example, I first want to just give you some general tips for solving problems involving one-dimensional motion, in other words, motion along a straight line, when the object is subject to a constant force. The first step is always to visualize the motion and draw a very clear picture, including a coordinate axis. You'll see that I did that on the preceding example, and I'm about to do it on our next example. Second step is to verify, before you start writing down formulas, verify that this is indeed a constant force or constant acceleration situation. Because if it's not, all those lovely expressions that we have for the position and velocity of an object simply don't apply. They only apply to constant force situations. If it is, in fact, and you verified that it's a constant force situation, then you go ahead and you write down the general equations of motion. You write down these equations. Now, if you are told what the value of the acceleration is, you plug that in. If you're told what the initial position is, x naught, you plug in that numerical value. And if you're told what the initial velocity is, you plug in that numerical value here and here. Okay? Once you've done that, then the next step is to see if you're told any additional information in the problem, and if you are, use that. And then once you've employed all the additional information that you may be given, then you're going to try to answer the question that you're asked. By the way, in problems that involve more than one object, you might have two moving objects. If they're undergoing constant acceleration, you simply write down the position and the velocity equations for each of those objects individually. Another thing that can also happen in slightly more complex problems is that you might have a problem in which there's a constant force that acts on an object, but it only acts for a certain part of the problem, and then the force stops and maybe a different force starts acting, or maybe no force acts. And so in cases like that, when the force is changing, strictly speaking, you can't use these equations because they only apply for constant force situations. But sometimes you can break up the problem into different stages, and if the force is constant during a particular stage, you can use these equations to describe the motion during that one particular stage. Again, these problem-solving tips probably seem a little bit vague at this point, but as we work through more examples and as you do more of the practice exercises on your own, revisit this list here so you can see how it actually applies. But now it's time for another example. We want to build up a lot of intuition here. So, consider the following. You're standing on top of a building. You take a ball and you throw it straight downwards, and it leaves your hand at 10 meters per second. And once it leaves your hand, it's just in free fall. You time it and you notice that it hits the ground 1 second later. Based on that information, you want to figure out how high is the building that you're standing on. So let's go ahead and use our methodology. Step 1, visualize the motion and draw a very clear picture that includes a coordinate axis. Okay, so we're on top of a building above the ground, and we're throwing this ball down at 10 meters per second. So here I draw a coordinate axis. Here, this point here represents the height of the building. It's at some height, y naught. I don't know what that height is. And here's the ball, and it's tossed down with an initial speed of 10 meters per second. Second step, verify that this is a constant force or constant acceleration situation. Well, once the ball leaves my hand, only the force of gravity is acting on it. We're ignoring any air resistance. So gravity is tugging on it, and gravity pulls down with a constant force. If you're close to the Earth, it's pulling down with an approximately constant strength force, and that causes a downward acceleration of 9.8 meters per second squared in the downward direction. That's what little g represents. Okay? So yes, once the ball leaves your hand, this represents a constant acceleration situation. When the ball is still in your hand and you're pushing on the ball with your hand, then no, gravity isn't the only force. You also have the force of your hand on the ball, and that may not be constant. So you can't use your constant acceleration formulas at that time. But we're going to analyze the problem from the instant the ball leaves your hand, so that the only force acting on it is gravity, hence it's in free fall, and hence it's undergoing constant acceleration. The next step is to write down the equations describing the position and the velocity, and if I know the acceleration of the object, I'm going to plug it in. If I know its initial position, I'm going to plug in that value, and if I know its initial velocity, I'm going to plug in that value. Okay? So here's the expression for the position, y, as a function of time, and for the velocity, the vertical velocity, as a function of time. Let's go through this expression here. The height at time t is given by the starting height. Well, I called it y naught. I don't know what that is. That's the height of the building. That's what I'm trying to find. The height at time t is equal to the initial height plus the initial velocity times time. Now, the initial velocity here, it's 10 meters per second, but it's downwards, which is in the negative y hat direction. So the initial velocity is negative 10 meters per second times time. And this last term here represents 1/2 the acceleration times time squared. Now the acceleration, it's 9.8 meters per second squared downwards because gravity is pulling down. So that's in the negative y hat direction. So the acceleration is actually negative 9.8 meters per second squared. And so if I take half of that, I get negative 4.9 meters per second squared. So this is 1/2 the acceleration times time squared. Likewise, here's the expression for the vertical velocity as a function of time. It's equal to the starting vertical velocity, which is negative 10 meters per second, plus the acceleration times time. And the acceleration is negative 9.8 meters per second squared. The minus sign is because it's accelerating downwards because gravity is pulling it down. Okay? So here's the expressions telling me the position and the velocity as a function of time. Next, if you're given any additional information in the problem, use it. Well, in this problem, we were given one important piece of information, namely that when the ball hits the ground, it took 1 second for it to get there. So it takes 1 second for the ball to hit the ground. So I want you to visualize that. It takes 1 second for the ball to get to there. So when it's on the ground, when it hits the ground, that means its height is 0. So let's go to this position equation, this height equation, and set the height equal to 0. So I'm going to set the height equal to 0, and I'll get, and we're told that it takes 1 second for it to get to that point. So I'm going to set the height equal to 0 here, and I'm going to plug in t equals 1 second here and here. And if I do that, I get this. And then if I solve for y naught, which represents the initial height or the height of the building, it comes out to be 14.9 meters. And then the last step is to look at what you're actually being asked to find and answer the question. In this example, we were asked to find the height of the building, so we've done that. The building is 14.9 meters high. There you have it.